In our paper, we propose to use the now state-of-the-art A3C algorithm to learn a common decentralized policy in a distributed manner on a single articulated robot. We focus on a case where different portions of a snake robot should enact the same policy based on different feedback from local sensors. This policy allows the snake robot to adapt its shape to external forces during locomotion to avoid getting stuck and maximize its forward locomotive speed. During training, a global shared network is concurrently updated by each of the low-level agents based on its own experiences obtained from the associated portion of the robot. The learned policy is finally shown to outperform the current state-of-the-art compliant controller by more than 40% in terms of forward progression. During locomotion in unstructured environments, a snake robot needs to be able to adapt its shape based on external forcing. In this paper, we consider this type of compliant control both on the amplitude of the sinusoidal shape of the snake, as shown in this first video, as well as on its spatial frequency or wavelength, which controls the number of sinusoidal waves, as shown in this second video. Recent results have shown the importance of decentralized control, meaning the capability to only deform the sinusoidal shape of the robot locally based on local sensing, to overcome obstacles without impacting the overall locomotion. In this paper, we build upon the fact that a homogeneous policy should be enacted in each portion of the snake robot, and we propose to learn this policy in a distributed manner by relying on the sum of experiences gathered from all the portions of the robot. Contrary to the initial definition of the A3C algorithm, where each worker agent learns in its own independent environment, we propose to let low-level agents learn in their own portion of the same snake robot. We devise an offline training approach, where workers randomly sample experiences of the associated portion of the robot from recorded runs of the state-of-the-art compliant controller. In this shared learning environment, agents asynchronously update the global network based on shared rewards, which quantify the forward progression of the snake based on the joint actions of the different portions of the robot. Finally, we implement the learned policy on a 16-degree of freedom snake robot and compare its performance with the state-of-the-art compliant controller in a randomized unstructured environment. Experimental results show that our learning-based approach outperforms the compliant controller by more than 40% in terms of forward progression. Additionally, the learning policy results in a decreased variance over trials, meaning that it is also more repeatable. We believe that this increased performance is due to the fact that our learning-based approach effectively allows for the main hyperparameters of the compliant controller to become time-dependent and therefore to better adapt to different situations.